Hello, good afternoon from Dallas, Texas, and to others around the world, it's good morning or good evening. Anyway, welcome to ICDE 2020. We will be just about starting the second keynote address of the conference. And this keynote address will be given by Dr. Sharad Mehrotra, professor from the University of California, Irvine. And his talk will be on Tuples Testbed Challenges and Opportunities in Managing Data for a Campus Scale Smart Space. I'd like to say a little bit about Sharad. Dr. Mehrotra, as I said, is a professor at UC Irvine. And he has had an outstanding career in data management. He received his PhD from UT Austin, and then he was on the faculty of University of Illinois at Urbana-Champaign before joining UC Irvine around 22 years ago. Dr. Mehrotra is an expert in data and management, in several aspects of data management. And he has published papers in top-tier conferences, including SIGMOD, PVLDB, ICDE, and many more. And he received the NSF Career Award, which is very prestigious. And he's also received several 10-year Test of Time awards, including at ACM SIGMOD in 2012, and also DASPA in 2014, where he had presented a paper 10 years prior on encrypted database query processing. In that area, Dr. Mehrotra is one of the pioneers. And also, he has done substantial work. He's a director of a huge center in UC Irvine and headed a project, a very large project called Rescue. And that's on emergency management preparedness, which has helped has had several applications. And so what's interesting about Dr. Mehrotra, he's not only outstanding in the theoretical concepts, his research has also been converted to practice. And so we are looking forward to hear him speak today. And so what I'm going to do at this time is turn it over to Dr. Mehrotra. So we have 1 hour, I believe, for this session. So he will talk for about, I don't know, for 50 minutes or so. And then please send your questions under the Q&A. If you go to Zoom, you will see Q&A. And so please type in your questions, and then I will read out the questions so that Dr. Mehrotra can answer the questions. Okay, so I'll now hand it over to Dr. Mehrotra. Sharad?
Thank you so much, Bhavani. Thanks for the kind introduction. So today I'll talk about the more recent work that we've been doing over the last 4 years on building a Tuples testbed. Can you hear me properly? Is that okay? I'm a little bit scared about the reception, basically, or the connectivity. I'm hoping it's okay.
I can hear you at least.
I can hear.
Great.
Right.
Let me know if you cannot. All right. So I'll talk about Tuples testbed. This is the work that's been going on in our group for, let's say, the last 4 years or so. This was funded by DARPA as part of creating an infrastructure for studying privacy technologies in the context of IoT systems. And it's part of a larger project called Brandeis effort, which DARPA had sort of initiated a few years ago, with the goal of studying whether privacy technologies have evolved to the level that you can build real applications and real systems based on this technology. So it's in that context I'll sort of give a talk. All right. Okay. So to motivate the application, I don't think this group needs much of a motivation on the importance of IoT. It is the next big wave. Today, if you look at it, there are over 25 billion devices which are connected worldwide, probably even more. And the expectation from the hype media is that it's going to reach in the order of trillions. This produces exabytes of data, and basically our community is the one that sort of manages the data. So it's an integral, a very important motivating application as for our community. And opportunities that such systems or IoT systems offers, they transcend every different domain, from healthcare to transportation to security and surveillance and so on, to smart infrastructure to industrial IoT systems and so on. So the goal of these systems is that if you can sort of have sensor technology to observe the physical world, then you can have a digital representation of the evolving physical world, which can bring in different levels of efficiencies, robustness, resilience, new functionalities, and so on. Now, while the landscape of basically IoT is huge, the one that sort of, given the context of privacy, the one that is sort of interesting from our perspective were human-oriented systems or human-oriented IoT systems. So the kind of things that were interesting to us was more towards smart spaces. So imagine that you have a digitized environment, a campus as it might be, and you can walk around the campus with your cell phone and connect with all the infrastructure, the buildings, the devices, and so on, with the help of your, let's say, a mobile machine or whatever it might be. And the infrastructure talks back to you, it customizes its, basically the environment for you and builds in new functionality. All right, so if we start thinking along IoT domain, there are several challenges, much of which has received a significant amount of attention from our community, specifically in the context of big data. And there's been a plethora of developments in the last 10 to 15 years in the context of dealing with basically very large volumes of data, and also data that arrives very fast. So things such as fast ingestion systems, time series stores, stream processing systems, poly stores to sort of make everything work together. All this stuff is going on in some sense. There are, in IoT context, the other three V's, like the other two V's rather, which are sort of equally interesting as well, probably take a new meaning to a certain degree. So the next V for us has been the variety. And typically, as in the sensing domain, there is obviously heterogeneity of the different sensors, but it takes a slightly more interesting context in our setting, in the IoT setting. For instance, in case of sensors, you can have basically sensors with overlapping capabilities. So if, for example, you're trying to locate somebody or localize sensors for presence sensing or location sensing, there are different choices that one can have, and these different sensors display basically different levels of trade-offs in terms of performance, the quality of, let's say, the task for sensing that you've got, even the privacy aspects of it, the cost of it, and so on. And incorporating that in the context of data processing turns out to be an interesting sort of challenge as well. Likewise for veracity. So we already know that sensor data can be very noisy. So there is an obvious concept of data quality. There's some early work by Franklin and group, which looked into RFID and sort of looked into data quality in the context of RFID sensing. Now, there are other aspects of it, which is sort of also interesting from the veracity perspective. And the concept that we have sort of focused on is the semantic gap kind of concept, where if you look at a lot of sensors, the kind of data that you get and the interpretation of, let's say, the real world phenomena or observations on top of that, let's say, sensor data, they're different. So you have to run some data enrichment code or maybe machine learning code to sort of interpret sensor data to basically make it usable from the perspective of, let's say, applications. And this adds another level of uncertainty into this picture. So handling such uncertainty becomes another issue of veracity as well. And then there's this final V, which is the V in the center of privacy, which is sort of also very important or interesting in this context. So you have to sort of worry about leakages through continuous streaming data of sensors, which observes the physical phenomena. So there are concerns that people can have in terms of, let's say, the capture of their behavior, cultural aspects, and so on. So continuous sensitivity is sort of, and I'll make a bigger deal of illustration of it a little later on, where a continuous stream of data can actually leak a significant amount of private information as well. All right, so here's what my talk would be. It'll consist of 3 parts, or I guess 2 parts. The first, I'll sort of lay out a journey over the last 4 years of building a campus level living laboratory, where the goal was to basically build a system which people can use. So the thought process here was that if we want to study privacy in the context of, let's say, a smart space system, we'll have to build an application and, let's say, a system which scales and which sort of works in the context of a campus on which applications are built. So we can actually look and observe and see to what degree do people use this and what concerns they actually have. So it's sort of a experience in building a, let's say, a system which is usable for a larger community of people. Now, as academics, there's not very often that we end up building, at least in my group, we've not sort of had too many opportunities to build systems which are usable, except for what Bhavani mentioned in the context of rescue, that we did something similar. But here we were fielding a system which people could use. And as a result of this, the considerations that go into sort of building a system span not just the technological aspects of it, but the other aspects. For example, the price, how much money you have to sort of spend so you can build actually a system. Those other issues also come into play. Whether people will adopt the system that you build or not. What's the deployability of the system? So there are other considerations that sort of drive research. And some of it is engineering, some of it opens up new challenges from the perspective of research as well. I'll talk a little bit about that, and then I'll talk about a couple of things that we have done in the context of, let's say, the Tuples system, which are at the boundary of different. So one example of this is the veracity problem. So we look into how we supported the system that we built to support real-time analytics. And another aspect is more towards the enforcement of privacy, and specifically for policy-based data processing. So we look into the issue of scale as well as, if time permitting, of trust. We might not get into the trust part of it. We may just look at the scale part. All right. So let me begin by talking about the Tuples testbed. So as I said, the view that we took of a testbed was that it has to be sort of end-to-end. So starting from a physical space where we instrument basically an environment with different sensors, build a system to data manage on top of it, build applications that people use, and then immerse people in the use of those applications with the hope that we can then study what's the value they get out of, let's say, the utility they get out of the applications, and to what degree does privacy end up playing, to what degree do privacy technologies sort of enable the utility still to remain high. So let me start with the physical space. The physical space we chose was UCI campus because we live here. That's sort of our campus. And those of you who have not sort of been to UCI are not that familiar with it. We have roughly about 300 buildings. There are about, on a daily basis, close to 50,000 people who are here. It's a residential campus with, let's say, about 2,000 faculty homes. There are 20,000 plus students who are in dorms living right here in campus. There are research park with hundreds of companies. There's a neighboring shopping complex. The reason I mention it is because it's also part of the UCI network, or the UCI network also works there. So it's a relatively large setup. If you think about it, it's like a community which is probably equivalent to a reasonable sized town, at least in the US. And the next question was, okay, what kind of, given this physical space to basically build a system, what kind of applications drove our work? And here are examples of it. So going back to the roots of rescue that Bhavani mentioned, one aspect of it was emergency. So imagine something happens at UCI or anywhere, like we live in California, there are earthquakes that happen all the time. And suddenly you have a need to evacuate. So you need to know at some reasonable level of granularity, how many people are there on the campus right now? Or for that matter, if you have, let's say, localized kind of a setup, then you might want to know in which buildings, how many people are there if you're trying to do evacuation planning. Likewise, there are other applications like context-aware messaging. So for example, a lot of you may know Chen Li. So let's say he is coming to office and I want to deliver a message to him. So, but I don't want a message to be delivered to him until he arrives in his office. So given the system sort of understands the context that Chen is in his office or coming to his office, that's when the message gets delivered. So context-aware messaging is yet another application that we found very useful in this. And these are just examples of a couple of applications, but there are lots of other applications that can come to mind right away. Besides real-time applications, we are also interested in analytical applications from basically from an educational perspective. For example, correlation between student performance and attendance. As professors, we hope that this correlation is there. Otherwise, maybe there's not too many point to classes. But that being said, this is one of the questions that is of interest to the education department to a degree, to understanding how students perform given their attendance. Likewise, there are questions from a behavioral science perspective. There's actually very nice work going on at Dartmouth by Andrew Campbell, where they're trying to study, let's say, correlations between observable behavior of students and depression. Now, that's something which, if I can observe students, for example, at some level, I can also we can study, let's say, such observable behavior and sort of look at this as early signs of, let's say, mental state or depression. And likewise, there are other sort of obvious applications which are understanding the optimizing space utility, HVAC usage, and so on of buildings. So those are the kind of applications, both real-time as well as analytical applications, that drove our work. And if you think about it, most of these applications revolve around some key sensing tasks. One of the tasks is that of presence. So where are people as a function of time when they're on campus? Or alternatively, occupancy. So given its location, space at some granularity, whether it's a building, whether it's a room in the building, a floor in the building, or the campus itself, how many people are there? So that's a fundamental sort of a question that one has to answer. There's also equivalently energy usage sort of, which is important to, or apportionment of energy, how much energy per user, per location. But today I'm not going to talk much about that. We're going to focus basically on presence and occupancy. Now, if you sort of want to have this key sensing task of presence and occupancy, you have to have the appropriate sensors. There are lots and lots of different kinds of sensors that can generate information about presence and occupancy. But the first obstacle one faces is that we're interested now in presence, basically not just outside where GPS can actually work, but also inside buildings. Now, if you look at it, over the last, let's say, 20 years or so, there's been a very large number of papers that have been written in census and large number of products which are all meant for indoor localizations using diverse technologies from RFID to Wi-Fi based systems to Bluetooth based systems to inertial sensors to combine to ultra wideband and so on, and combining all these things together as well to sort of come up with a robust representation of or robust detection of location of a person. We can probably get at this stage even in the order of, let's say, a few centimeter of localization. But if you think from our perspective, the localization technology can be divided into two parts. One is active sensing and the other is passive sensing. So active essentially is when the location of a person is sort of known at his device. So if I'm looking for location-based services, active sensing is sort of very useful. Passive sensing is where the infrastructure knows where you are without necessarily you participating or anything, you downloading any software on your device or whatever, but the infrastructure sort of finds out about you as well. Both of these systems that exist have significant weaknesses as far as we are concerned. If you look at, let's say, active sensing techniques that are sort of out there, this basically requires users to participate in localization. If you're building software which you're wanting to be adopted very widely, it's very difficult as academic institutions to sort of build applications which are that useful that people actually will download the software. So we have this huge trouble of adoption in reality when you do active sensing. If you go towards passive sensing, most of the techniques that sort of work well, they are pretty expensive. So they require basically dedicated hardware to be installed. For example, if you do, let's say, Wi-Fi sniffing, or if you apply RFID technologies, or let's say camera technologies, pervasiveness of that is limited, and also the expense is very high. So given limited budgets that we have, how would we ever go around doing localization inside the buildings? The good news for us is that most of the applications that we had in mind did not require very precise location inside. It just required it at the semantic level, or whether you're inside a room or whether you're inside a building or the floor and so on. And this can be achieved through basically the existing infrastructure of Wi-Fi that exists. So for example, in the campus, whenever you're connected to the Wi-Fi access points, the connectivity event of yours sort of raises an event, and this event can be trapped. It's actually already trapped and sort of forwarded to the basically the network infrastructure for network monitoring purposes and for diagnostics. One can sort of divert this information and collect it and then transform it and interpret it appropriately with some knowledge of where the access point is and what region it is in and who the device belongs to. And then you can interpret data to the extent that, for example, that John was in a given room at this particular time. So one can sort of use this Wi-Fi connectivity information for the purpose of localization, at least in the semantic level of room level and so on. But this raises already certain complexities. So for example, if you're using, let's say, localization using Wi-Fi, here's an example. Let's say you're connected to a given Wi-Fi access point, let's say number 3 right here. And the next reading that comes out is maybe you're connected to Wi-Fi access point 1 a little bit later on. The question is that there's a gap. If this gap is significantly large, where exactly were you, which access point were you connected to during this duration of time? So that's sort of like a missing connectivity information or problem or data cleaning problem that comes around right away. Even if you sort of go to the next level and say, okay, figure out a way to sort of bridge that gap. If I'm connected to a Wi-Fi access point, the region of coverage of access point is actually quite huge. So if you're trying to do, let's say, finer grained localization, which room you're in, you sort of have to address this issue of location disambiguation. So you could be connected to either, in this example, room 2018, 2014, and so on and so forth. So how do you determine which room you're in? So we built a system to address this thing. We built a system which basically uses a variety of different techniques from machine learning to sort of disambiguate your location at both the coarse level as well as the fine level. And we were able to achieve around somewhere close to around 85 to 90% accuracy. So given at any instance of time, we can guess for most people their location with the accuracy levels of around 85 to 90%. And that's reasonable for building applications. However, this comes at a cost, and that'll be the sense which I'll get to in a little bit later. So the cost of these machine learning models can be quite expensive. So specifically in our case, it takes roughly around half a second in the extreme case when you're sort of learning the model of a user over, let's say, a month of data to interpret, let's say, the location of this person. So it could take as much as, let's say, about 200 milliseconds to half a second. And you have to do this on the fly as the events arrive. So that could be expensive. Okay, so once we can localize you, we get to the second obstacle. The second obstacle is that of privacy. So if you notice, if I'm using Wi-Fi access point data, connectivity data, I'm actually not capturing any more information about you than what the system already does. So for Wi-Fi connectivity, you already are connected to the network. So we are just trapping that information for the purpose of localization. So in a certain ways, you may think that people should not be too concerned because there's no additional, let's say, loss of information or information being captured about them except for what they're already willing to share. But their concerns are but people did raise this concern. So this concerns that they come up because you're using this data set for an entirely different purpose of locating people inside buildings or in certain regions. And these concerns are well-founded. So here's a simple experiment that we did, or a study we did, where what we did was we took the Wi-Fi access point data sets and we anonymized them. So if you're you typically in a Wi-Fi access point data set, you identify somebody by the MAC addresses. So imagine you have sort of hashed the MAC address and now it's anonymized completely. So there is no knowledge of whose access point this particular thing is, even or this particular device is. But even with this, if you notice, pretty much the events such as starting of the day, people arriving at the building, end of the day, seminars, meetings, all this stuff is sort of hidden in the footprint of the data set, whether it's anonymized or not. Not only that, based on the behavior and expectational behavior of the people, we can actually do classification quite effectively. And specifically in this experiment, we were able to sort of identify who the residents were and even classify them as basically faculty, staff, and students, and so on. And you can also then learn social networks, basically which person hangs out with which person and so on. So there's a lot of information that's sort of hidden even in this anonymized MAC address, anonymized Wi-Fi access point data set. So why is this a privacy issue? So here's an example of a small study that we did. Imagine that I'm able to figure out who's the faculty and who's the student and so on. And now imagine in the context of a classroom, which I do have information about, that this particular class starts at 10 a.m. I'm able to figure out that this faculty person, because I've got a person's classified as a faculty, this faculty arrives to his class 5 minutes late. So I can sort of figure out the tardiness of faculty in their classes and so on. Then this can be essentially a privacy issue. Now, you do not want faculty to be tardy, that's fine. But the question whether others should be able to find out from this data set or not, that sort of is a privacy concern. And likewise, you can track staff and people who are, the amount of time people spend in the offices. All this stuff can be sort of determined quite easily, even on anonymized data. So the take-home message then was that we need stronger, basically, notions of privacy than anonymity. So what's the next best alternative? So the thing that is commonly we use is differential privacy. But in the context of streaming setting, which is where we are in the sensor setting, there's not much work that's happened basically in differential privacy. One of the best known work is a system called Pegasus, which is by Ashwin and Jerome and the group from Massachusetts and Duke. And here's a small study that we did on top of it. So here's an example where we took the live data set of ours, which is the basically sensor data set coming in from Wi-Fi access points. And the goal of this experiment was to sort of identify how many events of occupancy where more than 20 people sort of are there in a given week on whatever that occurred the week of May 11th. So in the particular experiment, we are dealing with one particular week of the time period and looking for events that have more than 20 people. Now, this is the data set with differential privacy or anonymized with differential privacy or noisy data with differential privacy. And this is the true data set. So as you can tell, it's almost impossible to do a task of this kind on differential private data set. So the concept of trying to sort of push differential privacy or other mechanisms to sort of deal with such noisy data sets becomes an interesting challenge. Actually, there's a paper, I think tomorrow in the 10 o'clock, session, where we are sort of looking at one-side differential privacy. I think EOS will be presenting this particular paper on trying to improve the performance of differential privacy to exploit partial sensitivity. Okay, so if DP doesn't work, what else can we do? So another thought is, okay, maybe we can use encryption technologies and we can enable use encryption in such a way that certain queries can be answered in ciphertext. But the problem with this model is that it's unclear exactly what privacy guarantees do you get. So you're able to get the true answers for certain queries. What's the leakage through the answers of those queries? And another complexity that comes around is scalability. So how scalable are going to be these encryption technologies? Can they sustain the rates at which the data is getting generated in the IoT system? And the answer turns out to be not at all. Like most of the encryption technologies that we do have, especially the ones that do offer relatively good security properties, are orders of magnitude slow as compared to, let's say, what data processing is in clear text. So there's a tutorial tomorrow in which Shantanu and myself and Anton will talk a little bit about advances in cryptography. So if we'll cover this a lot more in detail. Okay, the third possibility is actually push the burden of privacy back to the people themselves. So a policy-based framework. This is quite feasible in the sense that if you think of mobile world, this is sort of how people manage privacy quite a bit. So by having fine-grained user policies for acquisition, storage, processing, and sharing. But again, here the challenge becomes that of, and we'll soon see this, that there's a whole explosion of policies that happen. And that makes the policy framework sort of difficult to implement. And another key aspect of this problem then is building confidence in the system. So imagine a system promises to sort of follow the policy that the user has. How do we know that the actual system is actually following the policy? So the issue of trust comes into play as well. So there are challenges that sort of go around in trying to build systems of this kind. So that given the sensors, given the applications, we ended up there are quite a few different challenges that come around. And the system that we built, which is the Tipper system, is a scalable data management middleware, which attempts to address a lot of these challenges and embodies this concept of privacy by design. Tuples has now been deployed in quite a few places. Its main target was UCI. It was basically, it's been adopted at UCI to build a variety of different analytical and real-time services. It's also been transitioned to Honeywell, where they used it in the Golden Valley lab for basically building a building analytics application. Recently, last year, it was transitioned to basically to through NIVIC, which is the ex-SPAWAR. So through them, it was transitioned to and tested by Navy in the context of a Trident Warrior exercise, where it was installed on a naval destroyer and sort of to create a IoT space inside naval destroyer itself. So there are several applications that we have built in the context of using Tuples. Let me emphasize more recently in the last 1 month specific application that we ended up sort of transitioning Tuples towards. And after in the context of COVID-19. So when COVID-19 happened, or became prominent here in USA, then the campus decided to do a shutdown at that stage and basically implemented social distancing and so on. And this was a reasonable application from our perspective, given that we are able to sort of identify and locate people inside buildings at campuses. We could sort of build a variety of different social, very quickly transition Tuples into building social distancing adherence applications and crowd flow applications. Right now, we are also building a application which is based on contact tracing and exposure alerts. But let me show you a small video of an example of the use of Tuples in the context of COVID-19 for social distancing. So let me play this and see, hopefully it'll work. So what's being shown here is the concept of social distancing for us, the way we were sort of instructed was that in a given basically room with a given capacity, one way of implementing social distancing is to ensure that the number of people is a small fraction of the actual capacity. So what this thing is plotting in real time is essentially the number of people as a function of capacity in different parts of the building. So you can choose your dates or whatever it is. And the example that I was trying to show was that if you look at this I think is is March 12th. And if you look at the different buildings in the regions, it's all red because the buildings are very occupied right now. This is the day in which the chancellor sent out a message to us saying that, hey, we are implementing social distancing or isolation at this stage. And then if you sort of plot the same thing for the next few days, you can quickly see using Tuples now that people are beginning to adhere to basically the directives coming in from the chancellor, and sort of people are no longer using the building. We also built another application, is the Crowdflow application, which sort of traces the regions and identifies the number of people who have gone through a given region at a given instance of time. So imagine you have a location and you want to know in this region how many people have gone through in the last, let's say, half hour or last hour and so on. So it's an application that's sort of built on top of that. All right, so that's, let me stop the demonstration, move on. All right, so having built Tuples, let me now move to a couple of technical problems that we sort of we worked on in the context of Tuples. Okay. So the first system I'm going to talk about is EnrichDB. The goal of this was to address enrichment challenge in real time to support real-time data processing in Tuples. So let me get back to the example that we had. We get, let's say, Wi-Fi access point data set, and we run machine learning models to generate location of people or presence of people over time. And this is then used to create, let's say, maps of occupancy and build applications on top of it. Now, if I analyze the machine learning code that's running on top of it, these things take roughly around let's say in the order of around 200 milliseconds to even as much as half a second, depending on the complexity of the model that one is using. Now, if you look at the average, let's say, number of events in the campus, Wi-Fi events that happen in the campus, where there are roughly around 2,500 access points, the underestimate of this would be that there are about 3,000 events per second, which would then imply that if I were to sort of use this data set as it's coming in, as the event occurs, if I evaluate the location of a person, this is roughly going to take 10 minutes. And the question is, so at ingest, if you want to sort of enrich the data, per second of, let's say, per second of, let's say, ingest time, we have to have 10 minutes of machine time to run something like this. Now, for certain places, this might be reasonable, depending on the importance of sort of locating people as a function of time. One can buy additional hardware to make this thing successful. But as I said, the challenge here is not just the issue of, it's always the cost comes into play. So for us, that means it's not a feasibility. So if you sort of think of different strategies, enrichment at ingest in the context of, let's say, a system of this kind makes it prohibitively costly as far as we are concerned. The alternate solution is to do enrichment at the time of query processing. Now, this has also been explored specifically in the context of query-aware data cleaning, where you do not clean the data and you sort of let the data come in, ingested system sit in the raw format, and then basically analyze it later on and enrich it when the need for it arises. So if you think of data lake architectures, they sort of work along that direction as well. But this has also got a problem because it's got potentially unacceptable latencies. So what we decided to do was to, in EnrichDB, the system that we build, or we are building rather, the approach we took is to sort of enrich along the entire process of the data processing. So there's some parts of data enrichment that happens when the data comes in. There is some part of data that gets enriched intermittently, periodically. And then obviously there's some parts of it, depending on the query, that happens basically when the query is executing as well. And there are benefits for something like this. So we can sort of play around and optimize or try to reduce the ingestion latencies. They can optimize the quality of the query answering and so on. But this comes with a lot of challenges. So challenges are that you now suddenly have to maintain a state of the data itself. So because in determining, let's say, the execution strategy or the query execution and to enrich it periodically, you'll have to sort of maintain what is the state of the data. So state explosion can actually happen in terms of the amount of, let's say, metadata that gets stored. Then there's the issue of basically self-driving nature of the application or the system. What should we enrich at the beginning? What should we enrich at the intermittently? What should we enrich basically at the time of query execution? So furthermore, it requires a change to the way we execute queries as well. So this is the architecture of a sort of a EnrichDB, where there is a self-driving middleware, where data comes in based on the caching policies that are sort of there. The enrichment happens to a certain degree of, and the state changes happen to the system. And then when the query comes in, the query will basically use the existing state of enriched data. It may also partially enrich the data further to improve its quality. One of the things that we implement in EnrichDB is this concept of progressive queries. So query processing in this setting is sort of like is broken up into epochs, where each epoch consists of a think act cycle. So the think part of the system, we are sort of figuring out what do we enrich further, and the act part is executing the enrichment functions and therefore changing the state of the system, and then sort of this process continues on and on. So we have several, our initial architecture for EnrichDB was to layer it on top of existing technology, existing databases. Specifically, we chose Postgres. So the way it works is once a query comes in, based on the state, we end up figuring out what part of, let's say, the current relations given the state of relations, current state of objects, what part of the objects are clean enough that we can actually query that, we can actually generate an answer for the query. And based on it, we generate the initial answer. And after that, we sort of figure out for basically the remainder of the data, what will be the benefit be of enriching the data further, which generates a new plan. And then this process continues. So we then enrich a little bit of the data and then answer the query and then do the delta computation. And this process continues on and on until basically the user gets satisfied or basically the query ends. All right. Okay, so the way this works is, there are a lot of different challenges sort of in building a system of this kind, where how do you go around doing indexing of the state? How do you estimate the benefits? How do you layer this on top of materialized views and databases and so on? So let me show you again a functioning EnrichDB system and the way it sort of interfaces with the users. So here is the example where what we are doing is, let me stop it here and then tell you a little bit about it. So what we are doing is we are, in this case, we have a plot of a query. So you're looking at a given location. The location is a room, for instance, and you're plotting the occupancy of rooms as a function of time. Now, the occupancy or the presence of a person in the room is sort of not, is an uncertain attribute, for which you have around machine learning code that's sort of running behind the scene, which takes around half a second to run. So the way for each event, so the way the system works is that you initially get a approximate answer, and then as time goes on, more data is getting enriched, and as more data is getting enriched, the answer is sort of improving. So here's an example of the system sort of running. The key goal here is that the answer gets back to the user right away, basically, and it refines over time, as you can see. Here's another application of the same thing. Let me show you another one. In this case, the context is different, and the context is a multimedia database in which we have people, a database of faces and of people, and the query being run in this case is gender selection. So for example, you're looking in this images for all the, let's say, all the females. And there's a machine learning code which is sort of running behind the scenes, classifying people as males and females. And again, it does the specific thing that's running here is neural networks, sort of, which are different levels of neural networks, which are doing the classification, and they come at different costs. So the key whole thing again here is that the quality keeps improving as a function of time, basically. And let me show you the last one, which is there on tweets. So here there's example of tweet classification. So here again, the particular function that's running here is classification of tweets is based on sentiment. And again, as we keep running the system, the answer for the query results sort of keeps improving. So there's a classification that's happening behind the scene based on neural network again. In this case, classifying tweets is either positive sentiments or negative sentiments, and the results sort of keep changing as a function of time. And the right side plot is basically the improvement in the F measure and the quality that's happening as a function of time. So EnrichDB is, the goal of EnrichDB in this case is to basically ensure that enrichment happens on the fly. Okay, so let me shift gear and go to the next problem that we looked into, or one more problem that we looked into from a scalability perspective in Tuples. So the problem of scaling policy-based query processing in Tuples. So before I go there, let me briefly mention the role of privacy policies and how they work in a setting such as an IoT space. So a policy basically defines a condition under which users' data is captured, stored, processed, and shared in IoT space. Policies themselves can be of two types. They could be infrastructure policies. So for example, a building may state that anybody coming into the building during, let's say, off work hours will be captured with on let's say a camera system, for instance, from surveillance purposes. The policy could also be that of a individual or a person. So I may allow somebody to access my data for certain purposes at certain times under given a certain context. Or I may, given an infrastructure policy, I may express a preference saying that whether or not I want my information to be captured. So typically there is this trade-off, like if you, in an IoT setting, that in a smart space setting, that if you want a certain, let's say, location-based service, you have to share location. So for example, in Google Map, you can specify whether you want to share location or not. Depending on your preference, you may or may not be able to get certain service. So each of these are basically policies. A typical system, such as a smart space, will have to ensure something like notice and choice. So if there is a data capture policy that's out there, it'll have to notify the person of a data capture policy. It'll have to seek, let's say, consent from a person saying, okay, whether a person is actually willing or not to share the information or to share the sensor data or whatever it is, some personal data about themselves. So it'll have to be a consent which will have to be managed as well. The challenges in this case arise in both these things. So for example, we'll see in a minute, there's an aspect of explosion of policies in the IoT space. And furthermore, if you have a notion of consent, there has to be the question of trust arises, whether user will trust basically the infrastructure or not to implement the consent policies. Okay, so the most, let's say, relevant sort of prior work which is done in the context of privacy policies in the mobile world, so which we are all used to. So if you think of, let's say, cell phones and downloading applications in iOS or in Android, these systems sort of offer you opportunities for specifying your preferences on your policies with regard to what data you want to share. And the consent management, the consent concept has actually evolved over time. It used to be the case that basically when you install an application, you have to specify at the time of installation whether you accept to share data or you don't accept to share data. The only choice we used to have was either we accept it or we do not install an application. Since that time, things have evolved, and now basically applications offer you the opportunity to, at the time of the use of data, to whether to let the system know whether you want to share the data or you don't want to share the data. So for example, the example on the right-hand side shows Google Earth, whether you want to share location or you do not want to share location at the time of use itself. So the kind of policies that are there in the IoT world are something similar, where you want to let the system know whether it should capture your data or you should not capture your data. So let's look at an example of challenge that comes from a scale perspective. So imagine here's a policy. A policy is that a faculty teaching a class can access student data for attendance during class times. So that's a very normal policy that one would have in IoT space, or the kind of smart space that we are sort of thinking of. Here'd be an example of an instantiated policy. This is instantiated based on, let's say, Mike Carey teaching a class, his class on, let's say, databases, and there's a student called Alice. So the instantiated policy will say that, okay, Mike can have access to Alice's data under certain situations, basically if she's in the duration of during the time period of the class itself, and the location being the classroom, right? So the policies allow that. In addition, let's say Alice, let's say, works on Mike's research group, and she has additional policies for Mike to access her data at different times as well. And likewise, there are other faculty and staff who want to share data with Mike based on a variety of different purposes. Okay, and then Mike's PhD students also share the data about their location when they are at work, so that Mike can trace them down. So the question is, how many policies are there for Mike? If you think about it, if let's say there's a class has 200 students, there are 200 such policies that sort of apply to Mike at this stage. And if you add up all the policies from faculty, and let's assume he teaches 2 classes, it's not unimaginable that the number of policies that apply to Mike as the querier is roughly several hundreds to 1,000 policies. And if you sort of count the number of policies in the whole campus, for about 50,000 people who are sort of in the campus, this is in the order of millions of policies. So now the question is, a query comes in, let's say Mike asks a query, Q, and we are supposed to implement the query execution. So he's looking for, let's say, people in a given region. So how will you answer a query of this kind? So traditionally, the way the database systems will work is each of those policies would result in a rewrite of the query. So either the policies are represented in the form of a table as data, or by defining views. Irrespective, we'll end up rewriting the queries. And if I rewrite the query with the policies, so the where clause, the SQL query will sort of change, and it will sort of have the policy representation as well. So now suddenly the where clause has hundreds, if not thousands of conditions which are sort of hidden there. So how do we optimize a query of this kind? So if I sort of give a compiler, a SQL optimizer, a condition with thousands of, let's say, clauses in the where clause, typically the execution of that would hardly be able to exploit indexes, and it'll sort of run this as a linear scan on which these complex conditions will be tested. So one thing we did was we sort of simulated we simulated the policies, and we ran it on a benchmark which we have created called Smart Bench, which is a benchmark meant for IoT spaces or for smart spaces. And we calculated the amount of time it takes to run a query, in this case on Postgres. And depending on the number of policies, the time it takes in seconds for a real-time query can be in the order of around 15, 20 seconds, or 25 seconds. With around 300 policies or so, it was taking around 25 seconds. Clearly, that's not real-time anymore. And likewise, if you take a more complex analytical queries, the time increases to in the order of around 20 to 40 minutes of execution time, just to check the policies. So this is sort of a problem of scale. As policies increase in the IoT space, how do you answer queries in either real-time or analytical queries as well? So the thing we did was we built a system called Sieve. And what Sieve does is sort of, it exploits two basic ideas. So first thought is that if you look at, let's say, so the problem that's happening in scale here is you're testing for each object 2,000 different policies. Now the question is, can I reduce the complexity of number of checks that one has to do? So the most obvious thought is, okay, imagine basically a tuple that rises up to from a relation that's coming up. Instead of checking all the policies, if I sort of have the context of this tuple itself, such as who the person is and what the other contextual variables might be, I can actually reduce the complexity. Instead of checking all policies, I can check only a few policies. So I can, if my policies are sort of indexed themselves, I can use the tuple context to sort of cut down the number of policies that need to be checked. So that is the first optimization one can sort of have. The other thing you can do is we can cluster the policies into groups such that the tuples only need to be checked against a subset of these policies. So imagine that if I sort of factorize the policies, if I take some set of policies, cluster them together, and route only the tuples which basically have a potential of, let's say, being allowed by these policies, of making these policies become true. They are the only ones. So other policies which sort of do not overlap with these, other tuples that do not overlap with these policies can be culled away. So therefore, we can sort of improve this by putting optimization techniques. And sort of that's what we did. And so here's an example of it. So here's, let's say, a policy from filtering purposes. So let's say I have a policy which says, which has three different policies right here. One is user equals John and sometime whatever it is within this context. So if I sort of factorize this and I come up with, let's say, different factors, I can reduce the number of tuples. And once I do factorization, I can actually use indexes. And I can then use the index scan to sort of look at different and characterize different factorizations for the cost and sort of choose the best plan and therefore cut the cost of evaluation of the policies. So once we did this, the execution time of the same queries went from 20 seconds to around 0.5 seconds. And for analytical queries, it went to around 20 minutes to 40 minutes to about 20 seconds or 25 seconds. So there's a huge difference that can be done by simply trying to optimize for, let's say, dealing with large number of policies. And therefore, you can sort of overcome the complexity of that. Let me move on. Well, so what I did give was the basic idea, but the complexities come in as the policies sort of become more complex. What if they dynamically change? Then how do you layer this stuff on top of databases? And so on. So there are a lot of other complexities that I did not cover. Okay, so let me change and let me actually give you a 1 minute worth of auditability as well, and then sort of move on to the conclusions. Actually, I'm running out of time. So let me go straight to conclusions. So here are some concluding thoughts. So IoT is a rich and fertile area for database research. We sort of know that. There's been a lot of work in the context of building big data systems, but the problems because of variety, veracity, and privacy, they sort of add a new twist to the problem and make it, especially problems that are sort of at the border of, let's say, these different things. So for example, if you think of, let's say, a semantic gap, or if you think of, let's say, the privacy, making these things scale to have real systems that can actually scale to a, let's say, campus level scale, that opens up new challenges for us. And finally, a quick thought is, if we think of the style of research, very often as academics, we end up doing basic academic research, and this can be disruptive, but the danger is that it's sort of, sometimes you make up your own problems. The contrast of this is, the other side of it is the industrial driven research, where it's typically quite useful, but it risks being incremental from the academic perspective, because you're sort of solving the industry problems. So the thing that which I sort of appreciated or liked about the kind of stuff that we are doing is, if we end up creating living laboratories in the campus level, we are sort of not getting irrelevant. We are doing relevant, hopefully relevant research. And yet it is basically novel directions that you can pursue on your own. So there's a certain amount of excitement in sort of creating these situations where you sort of solve the problem from the perspective of, let's say, real world applications working in the campus itself. Finally, I would like to thank a lot of, this work has been the collaboration with a lot of different people. It's been funded by DARPA, NSF, Toshiba, and so on. There have been a bunch of research partners, and this is the team. And if you need more information, this is the website, tippersweb.ics.edu. There's actually a downloadable tipper system, which is there as well. So it's a Dockerized version. So if you want to use it, you can actually download it and use it as well. Last comment. Sorry, Bhavani, one quick thing. Yeah, I wanted to remind you of this thing. There's a course command which is happening in IIT Bangalore, India this time on January 2nd and 4th. There are a bunch of us who are in the committee, and we invite you guys to submit papers to this.
Okay, thank you very much, Dr. Mehrotra. Let's give him a hand. And we have time for some questions. I've only gotten one question, so I'm going to read it out, but please start sending your questions, okay? So this is a two-part question from Morad Uzani. So he says, Sharad, for EnrichDB, when deployed in the real world, how do we know that quality is improving, as you mentioned in the different examples? That's the first part. Then do you suppose you know the ground truth? So if you can answer both parts. So how do you know that quality is improving, as you mentioned in the different examples?
Right, so that's a good question. So in reality, so it's like to a certain degree, it's an assumption that the more you invest in terms of like having a more deeper model, the better the quality will get. You can, in certain situations, a training set is possible. So you can sort of observe this in a training set, and then sort of in the real time, you can sort of, assume that to be the case. You can do spot testing. It depends entirely on the situation that you're after. So in certain situations where it's possible to sort of spot test an answer and determine if the answer's quality is improving or not, you can sort of observe it as well. You can also learn these models on the fly using reinforcement learning.
Okay, in the second part, do you suppose you know the ground truth?
So either you have a training set for which you do know the ground truth, from which you can learn the stuff, or if you do not know it, then in that case, you have to make an assumption that at some stage, the quality, like again, through the iterative learning, the system can be learned, the quality can be learned, and at some stage, the user will specify the quality is enough. So,
Sharad, could you turn the video on, because they would want to see you, please?
Sorry about that. Yes.
Thank you.
Can you see me now?
Okay, sorry. Yeah, right.
Okay. Yes.
So yeah. So the second question you said about the ground truth, if you can.
Your audio disappeared, Bhavani.
Oh, the audio disappeared? No, I can hear you.
No, I can. No, it's back. No,
I
couldn't hear you. Sorry. Yes.
Okay,
Yeah.
so there's another question. Why didn't you use this is from Enamel Hake. Why didn't you use NoSQL database like MongoDB instead of EnrichDB Postgres SQL? Don't you think query optimization would have been better that way? That was also my question, but anyway, he has asked this question.
So the purposes of, so we layered it, EnrichDB on top of PostgresDB primarily because the Postgres SQL has a materialized view implementation. And Mongo would not solve, so the EnrichDB is a middleware. So it's not exactly tied to any specific, let's say, system underneath. In fact, one of the things that we are doing right now is actually building our own system as well, which actually does, let's say, enrichment on the fly natively as well. But it could have been layered on top of any database, which has support for basically materialized views. So we exploited the materialized view implementation of PostgresDB. Mongo would not suffice, a NoSQL database will not suffice because what we're trying to do is enrich on the fly. So the problem here is the cost of the execution is mostly based on the enrichment of the data. As I said, like let's say we take one event, let's say running a machine learning code on one event to properly properly localize a person takes about half a second. Now, Mongo would not solve any such problem, right? So like sort of this, it's more of a problem of enrichment as compared on computation as compared to, let's say, processing of the query.
Sharad,
that's that was good. It's a good answer, right? It's much clearer now. Murat, do you have a question? Yeah,
I do. I'll just ask live. Sharad, so coming to this policy framework that you mentioned, I'm just curious, like whether do you need such a complex policy framework? Because I'm not so sure whether end users will have, we tried in the past to develop such complex things for social networks and so on. So it looks like usability becomes one issue. So it looks like simpler to have a couple of simpler templates and enforce those kind of templates instead of allowing much richer policies for privacy purposes. Because at the end, users may not be using beyond anything what's default put there. So in other words, do we need such a complex policy enforcement mechanism that you are demanding?
So Murad, the policy and framework that we are thinking of is absolutely the question that having very complex policies that enable people to sort of write very complex policies makes it quite unusable, right? But if you think about it, a lot of the policies come from the infrastructure level itself. So for example, the example I was giving of policy from a class perspective, right? That would be a policy that is probably instituted by the institution itself, right? Like people can capture your data if you are whatever, like if you're teaching class, people can do attendance. So some policies come from there. I think the studies that have happened, for example, at CMU, they are collaborators in this work. Typically, I think about 60 to 70% of the people, they just will take the default policy which exists. Whereas there are few who are sort of privacy aficionados or whatever it is you call them. So they actually will go in and sort of set the policies. So much more fine grained policies. So effectively, I think the statistics is that about per application, per person, we have 3 settings. They do like 3 times you do the setting. And an average person has around, let's say around 25, 30 applications that they sort of have in their mobile phone. So setting up till 100 settings is feasibility for on an average per person. But if I sort of go away from the mobile world to, let's say, the difference, I'm not sure if it came across or not. So if you think of mobile setting, correct? The enforcement of the policy is done on the mobile phone itself, right? Whereas if you think of, let's say, IoT setting, let's say I have my data, you have your data, everybody has the data in centralized database, and somebody's running a query on top of all the data. Therefore, at the querier level, a lot more policies apply as compared to, let's say, so it's not that I'm setting more policies as a user. I'm still setting the same number of policies, but the number of policies that apply to me as a querier has increased. Does that make sense?
Yeah.
Yes, but I think we'll take it offline. To me, it's look like still the users, each of us may have a different policy, but we can group them nicely to get like a couple of policies apply in general. But let's take it offline. I don't want to take more time.
Right. So, any other questions? Okay. So I have a question. You talked about the privacy preserving aspects, right, of this of your system.
Right.
Have you measured the privacy? Do you have any metrics for the measurement, or is
Yes.
that something?
Yeah. Actually, yes. So I did not mention that word, but so if you, Bhavani, if you think of it, a, there are several things that you can do in terms of, let's say, implementing privacy, correct? So
Yes.
some of these techniques come with a sort of a guarantee of privacy, like differential privacy under certain assumptions provides you some guarantee, right? Usually this guarantee is a lower bound. So what it gives you is sort of like a good feeling about at least somebody's preserving your privacy, right? But it doesn't really measure the true privacy. Like actually how much privacy do I get? So one way to do this is to sort of take your mechanisms of privacy implementation you may have. It could be a basic anonymization. It could be any technique that you may actually, even let's say encrypted data search, and you're just answering queries on top of it, correct? So just giving you the answer to some queries and not to other queries, for example. So that's also a mechanism. So the question that's relevant here is, okay, how much privacy am I actually getting? And so we did a study recently, and what that study sort of compares is from a realistic setting, sort of how much privacy am I getting? And the way we sort of did this is as follows. Imagine that you have a prior, right? The prior is something which is without any data being released whatsoever, the amount of guessability a person may have, right? About, let's say, if I simply know you work at UTD and these are your office hours or whatever, these are the times you kind of come to work, I can make a guess about your location. Now, there's also, given whatever mechanism you've got, you can sort of determine the posterior as well, correct? So you have a posterior sort of a, given the posterior can be done based on complete data. If I give you, let's say, the counts of location, for example, I'm trying to determine privacy in the context of occupancy data, right? So if I give you the true counts, what will the guessability be, correct? And I can have you can throw in your machine learning code, whatever you want to in that setting. And then there is this mechanism of privacy sort of which offers somewhere in between. So now you can look at privacy as either a reduction from the extreme. So like the most amount of, let's say, violation of privacy to sort of how much do you get now? Or it could be like basically the gain of privacy. So for example, if I released all the information about you or about the counts, for example, correctly, what will have my guessability would have been, and versus for this metric, how much my guessability is. So we sort of just did a paper and a framework for doing exactly that.
Okay, that's good. So I don't think there are any more questions, but I just want to make a couple of, just a very quick announcement. There was a comment earlier, a question. Thanks for holding this conference online. It's a special experience. I'm wondering if the slides and audio of the keynote tutorial talks will be released afterwards. Yes, as we mentioned earlier, myself as well as Sudarshan, we are going to post all of the recordings, the video recordings, video audio on YouTube. And there are also some other special video postings. So we'll also post it on the conference website. And then there's one more announcement. The Alibaba special talk is going to actually start tomorrow, and we'll be emailing that to all the participants. It's going to start Wednesday morning, April 22nd at 7:30 a.m. Not 7 o'clock as I mentioned. It's 7:30 a.m. Central Daylight Time in the United States. Okay, so this brings us to the end of the session. And let's all give Sharad, just one, okay. One more comment, Murad?
Yeah, basically we keep updating the program. If there are any changes, just refresh the program for registered participants and you will get up-to-date information there.
Okay, thank you, Murad. So we are updating the program as changes occur. So thank you again, and let's give Sharad a hand. Thank you.
Thank you.
And then the next session will be starting, I think, what time, Murad? 1:30?
1:30 in 23 minutes.
1:30. Yeah, so 1:30 Central Daylight Time. And then, of course, we have tomorrow morning, the keynote sessions will start again tomorrow in the main webinar room. Thank you.
Thanks,
Thank you.
Thank you.
Thanks, Chad.
Bye.
Bye.
How do you